Hi, in this video, I will be showing you problem number 17 of chapter 16, section 7. Evaluate the surface integral. Double integral over S, x square z plus y square z ds, where S is the hemisphere, x square plus y square plus z square equal to 4, and z is more than or equal to 0. Note here we are going to find out the surface integral and surface integral over S, and S is the hemisphere given by the equation x square plus y square plus z square equal to 4, which is the center at the origin and radius 2. As z is given to be more than or equal to 0, it is upper part of the hemisphere. So how do you evaluate such an integral if S is a parametric surface given by a vector function r of uv? Double integral over S, f of x, y, z ds. Here note that this f is a scalar function. Because you will be seeing another formula for a vector field. So this f is a scalar function. So double integral over S, f of x, y, z ds equal to double integral over d f of r of uv, then absolute of ru cross rv dA. D is the parametric domain of S. So first in this case, we shall parameterize the given surface. Because it's a sphere, it makes sense to parameterize it using the spherical coordinates. So x square plus y square plus z square equal to 4, and z is positive, more than or equal to 0. We will use spherical coordinates as the radius of the sphere is 2, rho in the spherical coordinates will be 2. So x equal to 2 sine phi cosine theta, y equal to 2 sine phi sine theta, and z equal to 2 cosine phi. So usually it is rho sine phi cosine theta, where rho is the radius of the sphere. Here rho is the radius of the sphere, which is 2 in this case. So we are replacing rho by 2, where the parametric domain will consist of the parameters phi and theta. It's d all those phi comma theta, where phi lies between 0 and pi by 2 because it's hemisphere. So it goes only up to pi by 2 because z is positive, greater than or equal to 0. So phi starts at 0, ends at pi by 2, and theta is just like polar coordinates theta, which is 0 through 2 pi. So r of phi comma theta, which is equal to 2 sine phi cosine theta I, that's like xi plus yj plus zk, where x, y, z are replaced by these values here, which are written in terms of phi and theta. So we'll call that as step 1. Next, r phi is partial derivative of r with respect to phi is obtained by differentiating r with respect to phi, which is 2 cosine phi cosine theta I plus 2 cosine phi sine theta j minus 2 sine phi k. We call it step 2. Then let's similarly find out r theta, r sub theta, which is partial derivative of r with respect to theta, which will be negative 2 sine phi sine theta I plus 2 sine phi cosine theta j plus 0 k. We'll call it step number 3. So r phi cross r theta is the determinant. First row is I, j, k, standard basis vectors. Then the next row is the components of R5. The third row are the components of R theta, R sub theta. The third row is negative 2 sine phi sine theta, 2 sine phi cosine theta, 0. We'll call it step number 4. So R phi cross R theta, expanding this determinant, we get using the first row, ijk, expanding the determinant, this is what we get. So R phi cross R theta would be 4 sine square phi, which can be taken out, cosine theta I plus 4 sine square phi sine theta j plus 4 sine phi cosine phi, which are common factors. Then inside you will have cosine square theta plus sine square theta, which will be 1 by Pythagorean identity. So this is R phi cross R theta. Now we are going to find out the length of this vector, R phi cross R theta. It's a square root of x component square, y component square plus z component square inside the radical. We call it step 6. So it shall be, by simplifying that, it is 16 square root of 16 sine to the power 4 phi cosine square plus sine square theta, which is 1, plus 16 sine square phi cosine square phi. Now in this one, if you again common factor 16 sine square phi, inside we'll have sine square phi plus cosine square phi, which is equal to 1. So you get square root of 16 sine square phi or 4 sine phi, because phi lies between 0 and pi by 2. So it's positive. So square root of sine square phi is absolute sine phi. But absolute sine phi being positive, it's 4 sine phi. So we got an expression which is part of the formula. So that is step 8. Now coming back to the formula, and we use x equal to 2 sine phi cosine theta, y equal to 2 sine phi sine theta, and z equal to 2 cosine phi, you get x square plus y square, because it is part of the integrand, which is 4 sine square phi cosine square theta plus 4 sine square phi sine square theta, which will be 4 sine square phi times 1 by Pythagorean identity. So x square plus y square is 4 sine square phi. So in this problem, we have chosen phi and theta in place of u and v, the parameters, in the formula. So it is double integral over s f of x, y, z ds. equal to double integral over d f of r of phi comma theta, which is parametric form, then ds is absolute of r phi r sub phi cross r sub theta dA, which is the length of that vector. Just double integral over s f of x y z ds equal to double integral over s x square z plus y square z ds, which is what the problem is. We're taking z out by as common factoring. It's x square plus y square times z ds. So using all the expressions that we found in terms of the parameters phi and theta, substituting them, so it is double integral over the parametric domain D. We have x square plus y square, that is 4 sine square phi from step 9, then times z, which is 2 cosine phi, times ds, which is this one, absolute of r phi cross r theta dA, which is 4 sine phi d phi d theta. We'll call it step number 10. So it's 32 integral 0 to 2 pi d theta, and then theta phi running from 0 to pi by 2. We can break the integrals as one for theta and one for phi in this case, because one is independent of the other. They are definite limits as well. So this will be 32 times 2 pi. This is the third part of the integral is a very simple u sub. If you substitute sine phi equal to u, cosine phi d phi is du. So which will be sine to the power 4 phi over 4 between the limit 0 and pi by 2. So 64 pi times 1 over 4, which will be 16 pi. So keep in mind this problem is the surface integral for a scalar function. So next we will be discussing the surface integral for a vector field. So there will be a modification in the formula. Hope this video helps.